The key to understanding logarithms is to recognize their relationship to exponential equations. If our exponential equation is b to the a equals n, then the b is the base and the a is the exponent. So if we say 4 to the third equals 64, we mean that 4 times 4 times 4, or 3 factors of 4, are 64. The logarithmic equation log base b of n equals a is the inverse of our exponential equation. The b is the base, and it's the same base that we see in the exponential equation. And the a is the same exponent that we see in the exponential equation. Log base 4 of 64 is 3 for exactly the same reason that 4 to the third is 64, because 4 times 4 times 4 is 64. So let's take a look at an exponential function and see how it's related to its logarithmic inverse. For the function y equals 2 to the x, let's take a look at some xy pairs that make that equation true. When x is negative 2, y is 2 to the negative 2, which is 1/4. When x is negative 1, y is 2 to the negative first, which is 1/2. When x is 0, y is 2 to the 0, which is 1. When x is 1, y is 2 to the first, which is 2. And when x is 2, y is 2 to the second power, which is 4. We can look at those xy pairs in terms of domain and range. So when x is negative 2, y is 1/4. When x is negative 1, y is 1/2. When x is 0, y is 1. When x is 1, y is 2. And when x is 2, y is 4. So we see input and output pairs for our exponential function. Now let's look at the logarithmic function y equals log base 2 of x. It's the inverse of our exponential function. Because it's the inverse of our exponential function, our inputs and outputs will be reversed. So for our log function, an input of 1/4 will give us an output of negative 2. An input of 1/2 will give us an output of negative 1. An input of 1 will give us an output of 0. An input of 2 will give us an output of 1. And an input of 4 will give us an output of 2. Here's what that looks like in table form. For x equals 1/4, the log base 2 of 1/4 is negative 2. For x equals 1/2, the log base 2 of 1/2 is negative 1. For x equals 1, the log base 2 of 1 is 0. For x is 2, the log base 2 of 2 is 1. And when x is 4, the log base 2 of 4 is 2. Now let's take the ordered pairs for these two functions and see what they look like on a graph. One thing we can notice is that the two functions are reflections of each other across the line y equals x, and that's what we expect to see for inverse functions. We can also see something about the domain and range for each of these functions. For y equals 2 to the x, the domain is all real numbers. We can find points on the graph of y equals 2 to the x that have any x coordinate. The range of our log function is the same as the domain of our exponential function, so it's also from negative infinity to positive infinity, or all real numbers. The range of our exponential function is from 0 to infinity, not including 0. In other words, only positive real numbers. So the y-coordinates of the points along y equals 2 to the x will remain above that horizontal asymptote. In other words, they'll be greater than 0. The domain of the log function is the same as the range of our exponential function. We can see in the graph that the y-axis is a vertical asymptote for the log function. That means that the x-coordinates of the points along y equals log base 2 of x are always going to be greater than 0. So that leads us to a generalization we can make about the domain of any log function. If the log base b of n equals a, then we know that the n, the thing we're taking the log of, has to be greater than 0. This restriction on the domain of a log function is something we'll have to consider when we're solving log equations. Another restriction to keep in mind is that the b, the base on the log, also has to be positive. That's because the base of an exponential function can't be 0 or negative. If we're asked to evaluate a log function, we're trying to determine a number, a value that it represents. It's often easier to do that when we think of the related exponential function. And we'll do that by saying that the log base 4 of 16 is equal to some value x. We just don't know what that value is yet. But now that we've got this written as an equation, we can rewrite it as its equivalent exponential form. So if the log base 4 of 16 is x, then 4 raised to the x power is 16. We're trying to solve for the x, and if we recognize that 16 is 4 to the second power, then that's pretty easy to do, because if 4 to the x equals 4 to the second power, then x has to be 2. In other words, the log base 4 of 16 is 2. How about the log base 1/2 of 8? We'll do the same thing. We'll say that equals some value we'll call x, and then we'll use that equation to rewrite it as an exponential equation. 1/2 raised to the x power has to equal 8. 1/2 is the same thing as 2 to the negative first power, and 8 is the same thing as 2 to the third power. Now we'll use a property of exponents on the left side. Because we have a power to a power, we can multiply the powers and say that 2 to the negative x equals 2 to the third power. Since our bases are the same on each side of the equal sign, the exponents have to be equal as well. So negative x equals 3, or x equals negative 3. So that means that the log base 1/2 of 8 is negative 3. Now let's try to solve an equation that has a log in it. Log base 3 of 81 is x. If this looks a lot like the last two examples, you're right. We can rewrite this as an exponential equation, work to get the bases the same. 81 is 3 to the 4th power, and that means the exponents have to be the same. So the log base 3 of 81 equals 4. Log base 2 of 32 equals x minus 1. If we rewrite this as an exponential equation, we can say that 2 raised to the x minus 1 power equals 32. If we rewrite the 32 as 2 to the 5th power, we now have bases that are the same on both sides of the equal sign. So the exponents have to be equal. X minus 1 equals 5, which means x equals 6. So 6 is the solution to our equation. What if we'd like to solve log base 5 of x equals 3? This one looks a little bit different, but our method for solving it will be the same. We'll rewrite this as an exponential equation. So 5 to the 3rd power equals x. And since 5 to the 3rd power is 125, that means x is 125. Let's solve log base 3 of x plus 4 equals 2. Once again, if we rewrite this as an exponential equation, we'll be able to solve it. So 3 to the 2nd power equals x plus 4. 3 to the 2nd power is 9, so 9 equals x plus 4. And subtract 4 from both sides of the equation to get x equals 5 as our solution.